Hey everyone, and welcome. Today we're jumping into some seriously cool research about a brand new super material. And believe me, this one promises to solve one of the biggest headaches in our daily lives: why it takes forever to charge our devices. You know the feeling, right? You plug in your phone, your laptop, maybe even your electric car, and then you just wait. The problem isn't your charger, it's the fundamental way our devices store energy. But what if there was a material that could completely change the game? Okay, so to really get what's going on here, let's think about energy storage devices as two different kinds of athletes. You've got batteries on one team and supercapacitors on the other. They're both really good, but at totally different things.
So, a battery is your marathon runner. It's got amazing endurance. It can store a ton of energy and release it slowly over a really long time. A supercapacitor, that's your sprinter. It charges up in a flash and gives you this huge, instant burst of power, but it gets gassed pretty quickly. The trade-off is that it can do that sprint over and over and over again, thousands of times without wearing out.
So the ultimate goal, the holy grail for scientists, is to create a new kind of energy athlete, one that has the best of both worlds. You know, a device with the long-lasting endurance of that marathon runner, but also the explosive, instant speed of a sprinter. To build an athlete like that, you can't use the same old stuff. You need a brand new ingredient. Researchers are on the hunt for materials that can break these old rules, and the secret to all of this lies in one absolutely critical component. And that component is called the electrode. You can think of it as the muscle of our new energy athlete. It's the part that actually does the work of holding on to the electrical charge. So it's simple, really. If you want to build a better battery or supercapacitor, you've got to build a better electrode.
So what do you make this new super electrode out of? Well, the old school gold standard is a material called ruthenium oxide, but the problem is it's crazy expensive and needs some pretty harsh chemicals to work with. But this is where manganese steps in. It's cheap, you can find it everywhere, it's good for the environment, and it's way safer to handle.
And that brings us right to the star of today's show, a new compound these scientists cooked up called manganese malate, or M&M for short. They had a hunch that this specific combination could be the breakthrough they were looking for.
So how did they test it out? Well, they basically set up a competition, like a scientific bake-off. They used a really clever process to create 3 slightly different versions of manganese malate, just to see which recipe would come out on top. The process is called electrode deposition, and it sounds complicated, but the idea is actually pretty straightforward. They take a piece of stainless steel foil, stick it in a chemical bath, and then zap it with an electric current. By tweaking the voltage of that current, they can actually control exactly how the manganese malate grows onto the foil, creating their electrode.
And here's our first contestant. This is a super zoomed-in microscopic image of M&M2, which was made using just 2 volts. If you look real close, you can see it's made of all these tiny, granular nanoparticles kind of clumped together. And that unique structure is all thanks to that specific voltage.
Next up, we've got MM3, this time created at 3 volts. Bumping up the voltage changed how the material grew. The structure is still granular, but you can see the clusters look a little bit different. The point here is that a tiny change in the recipe can create a big change in the final product.
And finally, here's contestant number 3, MNM4, grown at the highest voltage of 4 volts. And again, you can see with your own eyes that the structure is just different. So now we have our 3 contenders, each one made with a slightly different recipe. The big question is, which one is the champion?
This is where the real test starts. It's the moment of truth. The researchers put all 3 of these materials through a whole series of tough tests to measure exactly how well they could perform. And wow, the results are just crystal clear. Let's focus on the graph on the left for a second. The higher the curve, the more charge the material can hold. You can see that black line, which is our 2-volt sample, MM2, is way above the others. Now, look at the graph on the right. This shows how well they held up after 10,000 charge cycles. And again, that MM2 line is almost perfectly flat at the top, which means it lost basically 0 performance. Let's put some hard numbers on that to see just how big the difference is. We're looking at specific capacitance, which is just the main way you measure charge storage. MM2, our 2-volt winner, clocks in at 186 units. MM3 is close, not bad, at 178, but then look at MM4, the one made at the highest voltage. Its performance just falls off a cliff, down to only 72. It's not even a contest. MM2 is the clear winner. And that incredible durability we saw? Well, after 10,000 charge and recharge cycles, MM2 still held on to over 97% of its original power. That is just amazing. That's exactly the kind of long-lasting performance you'd want for a real device you rely on every day.
So what was the secret sauce? Why was that 2-volt recipe so much better than the others? Well, the science really boils down to two things. First, the way it grew created more active sites. You can think of those as more parking spots for energy to be stored. And second, it had lower internal resistance, which is like having wider, clearer highways for that energy to travel on, letting it charge and discharge super fast.
Okay, this is all fascinating science for sure, but what does it actually mean for you and me? Let's zoom out a bit and see how a discovery like this could really shape our future.
And here's the kicker. This isn't just some lab curiosity. The researchers say right in the paper that their MM2 material performs as well as commercial activated carbon. That's the stuff that's already used in many supercapacitors today. So this isn't science fiction. This is a legitimate contender for real-world use.
And the potential here is just massive. I mean, imagine electric cars that could charge up in minutes instead of hours, or wearable tech like your watch that lasts for days and then recharges in just a few seconds. We could even use it on a huge scale to store energy from wind and solar, making green energy available around the clock. This is the kind of future this material helps make possible.
So we end up with this really exciting question. We have this new material made from cheap, safe, and common elements that shows truly incredible performance. Could this be one of the key ingredients for building our energy future? It's discoveries just like this one happening in labs right now that are laying the groundwork for a faster, more sustainable world.